Hello everyone. Just confirm if I'm audible, visible to everyone. I'll just check it from my end as well. Okay, hoping I'm pretty much audible to everyone. Guys, we have just started, so there was some technical issues, so we got a bit delayed there. I'm hoping I'm pretty much audible and visible to everyone. So I'm just waiting for a few comments, so probably then we can start. So today, Rod is to talk about how we can have the NLP process being done, so natural language processing. So we'll be talking about the advancement in NLP, where we'll be having a quick discussion around the topics where individually how we can still do the natural language processing. We have smaller components there. So I'll probably, instead of giving you the whole theoretical concept, I'll be talking in terms of the use case. So I'll be also showing you the code base for all of this. And I'll be in fact running you through a notebook. And during that notebook itself, I'll be showing you all the different concepts which is pretty much required in NLP. So we'll be doing all those parts today, guys. So pretty much I'm open to all the questions. Hey, Pawan, thank you so much for joining us. So practically, I'm pretty much open to all the questions. Let's make the class more interactive. So I'm very open to have all the questions. So I'm also monitoring the chat. So you can start posting your questions and anything, guys. So let's make it more interactive and we'll try to get benefited likewise. Okay, so just to give you a brief, my intention to cover the topic today is towards the natural language processing. I'll first cover the important areas, the key jargons, what we have in NLP, and I'll be showing you how we end up implementing on Python as well. And then eventually, once we are done with the basic implementation of NLP, like the basic use cases, then I'll be talking about what else. Now, what kind of new things are coming up? You might have heard of ChatGPT, the natural language models, LLMs, large language models, and we have BERT coming into picture. We have, in fact, transformer models also working on the natural languages. So all of this we're going to be talking about, and we'll deal with the concepts of how those works. Obviously, those are individual subtopics which can be taken up with time. But my intention is to show you the NLP process, how the core logic of NLP works. Once I have a text, so how do we process it? What are different concepts are there in NLP? So we will be pretty much talking about that in detail. Okay. Cool, guys. So as I've said, I'm pretty much monitoring the chat as well. So I would really want people to be interactive. So that makes the class more beneficial for everybody, right? So I would want people to be more active. So please feel free to reach out to me. So I am monitoring the chat. So I'll be looking forward to that. So any questions, anything, please feel free to put up in the chat, and I'll try to answer it as if it comes. Cool. So on that note, guys, let me share my screen and we can get started. But even before doing that, okay, let me first share my screen, then we'll start talking. Okay. I'm just sharing my notebook here. Okay. Okay. Everyone, I'm hoping you can see my screen. Just you can just give me a confirmation also if you are able to see my screen. So you can probably give me a quick thumbs up if you can see my screen. I'm writing it up here. I'm hoping it is visible. Yeah, I could see it's visible. Okay, my first topic. So, what we will be discussing today is going to be NLP. Okay, so where now we'll have to first understand what is NLP, right? Natural language processing. Yeah, thank you so much for confirming. Yeah. So, anyone wants to answer what you understand by natural language processing? Brinda, anyone else? Pawan? Uh, anyone? What do you understand by natural language processing? It's a natural language. I mean, for a human, a natural language is what I speak. So probably I'm speaking in English right now. So for me, the natural language of communication, the mode of communication is this English language, right? But is the machine understanding what I'm saying? Probably not, right? So it has to be processed. So the natural language for a human, which is probably any language, like any mode of communication, probably Hindi, English, Kannada, Tamil, Telugu, Bengali, any language, that has to be processed. And in fact, yes, absolutely correct, Nandini. So we have to make sure that language, which is pretty much human understandable, need to be communicated to computers or devices. They have to get that logic of what we are speaking. And ultimately, with the help of that, we need to get the crux. Like, absolutely correct. Interaction between computer and human, yes. So I need to process what I'm speaking. I need to make sure the system understands what I'm speaking. Right? So things become really important in that perspective. Okay, so I need to make sure I have my machine, whatever I'm using right now, they're understanding ultimately what I'm trying to say, what I'm trying to communicate. So that is pretty much called as natural language processing. So the phenomenon or the processes in which I'm trying to actually consume the natural language which I'm speaking, probably in terms of Hindi, English, or whatever languages, for the machine to understand that. So all those techniques, the strategies which I'm talking about comes pretty much under natural language processing. Okay, I'm going to quickly share my probably a whiteboard kind of a thing so that you can understand things in detail. Okay, just give me a minute. I'm sharing my other screen. Give me a minute. Okay, I'm sharing my white. Okay, can everyone see this whiteboard? I'm scribbling here. Is it visible? Yeah, I could see that. Yeah, it's visible. So, okay. Now, a quick thing, what we have understood here. So, first is talking about the natural language processing. So, we have understood where we are trying to process the human language. What do we have? So, more like I have a human language and I want the machine to understand this. Right? So how can we get this done? So probably whatever I'm speaking maybe in terms of the text which I'm talking about. Say my name is Arpit Jain, right? So it's a text. So probably it consists of words, and words obviously consist of characters, individual characters, the alphabets, and this multiple words ultimately frame up a sentence. And this sentence, multiple sentences probably make up a paragraph. And this paragraph probably end up making a document. Right? So that's how the individual crux of things are. So I'm going to talk about probably the individual words which I'm speaking right now, clubbed together, making up a sentence, and then sentence ultimately making up a paragraph, then a document. Right? So if I talk about a word as one reference point. So if word is my reference point, what is the smaller component of this? Characters, individual letters. If I take sentence as my reference point, that's where the words become my smaller components. If I take paragraph as my reference point, probably a sentence becomes my smaller component of that. So every individual components of any of this which I'm talking about has an individual building block to that. Right? So whenever we start doing anything, I'm going to show my code now. There's a concept called as tokenization. So very first step, I'm going to say a sentence. So probably I'm going to add up a new screen. Just give me a minute. I'm going to add up a new slide. Yeah. Yeah. So for example, I say a sentence, which is this. I have a sentence S, which says my name is Arpit Jain. Correct? So if I want to process this information, if I want the machine to understand what I'm talking, practically that means first process this entire information. So the very first step of NLP is called as tokenization, where what we do, we break the bigger chunk into smaller pieces. So if you see here, this is a sentence, and I know for a sentence, the smaller piece are my individual words. So if I perform a tokenization here, this sentence is going to give me a list of words, probably my name is Arpit Jain. So this sentence is practically having 5 words. And within this 5 words, now further sub-actions, I'm going to talk about certain grammatical interactions, certain punctuations. So all those individual sub-concepts comes into picture. There's a whole set of process which we still do. So always remember, my end objective is to consume this text to make sure the machine understands what I'm talking. So the logical first step is you break the bigger piece into a smaller piece, which is going to talk about here tokenization. And for a sentence, the tokens are called as words. And if I would have been talking about words, probably if I want to split this name into my characters, individual tokens, I will get NAME as 4 individual characters. But obviously that will not make any sense. So if I have to take out some logical meaning of this sentence, probably I need some words. So the words which is making this sentence, which is called as also tokens here in this case. So my name is Arpit Jain, what I'm going to talk about. Okay, so I need to extract this piece of information. So my first step here becomes tokenization. Okay, so likewise, I'm going to talk about multiple different things as well. So we'll be having different pieces. So we will be talking about multiple different things. So first, I'm going to be saying how we can clean this data. So we have a concept called as data pre-processing. So we have practically seen that for any numbers, for any classes, we have been cleaning our data, right? So probably a missing value treatment, an outlier treatment, a correlation check. So for text, for a natural language, which I'm using right now, what kind of cleaning processes I could have? So if you logically think, so probably some punctuations removal, I might have some excessive words which are represented like smaller words like is, are, am, the. So probably this can distort the whole meaning. So we can remove them. So they are called as stop words in NLP. So we're going to remove those stop words. So all those subtopics gonna be coming here in the next implementation part. So I'm going to showing you all those individual now sub pieces where I'll be cleaning the data. And all of these cleaning steps will have certain meaning, and how we are going to consume it, I'll be showing you on the code as well. So let's get started, guys. Now we'll quickly see the code implementation of things. Okay, so let me share my coding screen and then we'll get started. So I'm expecting people to probably have the notebook installed. Obviously, I want the notebook to be there. And if you can quickly open the notebook, we can consume it. So I probably, in fact, you will see I have already run the code. So you will be seeing the codes handy, but I'll be anyway sharing with this repository. So you can probably access it. So you'll be easily available for you also. Cool. So in Python, if you have to work on NLP, there's a package called as NLTK, Natural Language Toolkit. Okay. So the Natural Language Toolkit, the package which we have in Python is going to be working on the natural language perfectly fine. And we have all the sub-components which we have just talked about pretty much available inside NLTK package, and we'll be using it. Okay. And if you remember, I was talking about the stop words part. So stop words basically are those where the words are overrepresented, more like conjunctions, the connectors in a sentence, more like of, in, am, are, the. So obviously without them, the sentence will not make sense, but that are not the actual main pieces of my sentences. Suppose if I say, my name is Arpit Jain. So even if I remove is, so my name Arpit Jain, I'm still able to get the meaning of it. So is does not play a logical role in terms of the meaning interpretation, but probably to frame up a grammatically correct sentence it is required, right? So, but here is does not have its own importance in terms of the logical meaning of my sentence. So even if I keep my name Arpit Jain, I'm still able to understand what I'm saying, right? So that is where the stop words components comes into picture. So they might hinder the overall analysis. So generally in NLP process, we end up removing those stop words. So in NLTK package, you're going to be seeing this stop word present under NLTK corpus. So we're going to be using it. So now I'm going to start with the very first concept, tokenization. So tokenizing, as I've told you, the process of tokenization is to convert or break a larger piece of my text data into smaller sub pieces. So if it's a sentence, I'm going to break it up into words, right? So here, as you can see here, what I'm doing, I'm practically calling the word tokenize options. And in fact, in NLTK package also, I have multiple tokenization options. Okay, I'll be showing you multiple pieces of them. So first is my word tokenize, because I have a sentence here. I love my country, and I want this to be consumed into smaller sub pieces, which is basically my words. So I'm going to use a word tokenize. So this, the moment I'm going to call a word tokenize function on top of it, is going to give me I love my country. Right? So you can see this, a list of words, a list of tokens. So these smaller pieces are now being called as tokens. Tokens are nothing but the words of my sentence. So we'll be using it on top of it. And you can see multiple other types of tokenizations are possible. We have a tree band tokenizer, and you'll be seeing multiple other things as well. So, and all of this will have certain challenges, pros and cons. For example, this is very easy to split up. I don't have any punctuations, but you can see here, the moment I'm adding a punctuations, hello, comma, how are you? And can you see this? This comma is also getting used as my word, which practically I don't want. Right? And for example, here, why don't you come here? And you can see this apostrophe is coming up here, and look at the split up. Can you see this? It is giving me a wrong tokens. So to help them, to help these issues getting rectified, so I have multiple other functions, multiple other types of tokenization. In fact, I can write my own custom function also. If you realize, it is basically a split which is happening here. You agree? It is basically a split function. Split based on space. This is what is happening, right? Split based on space. So I can write my own custom function also to get the individual words. It's absolutely fine. There's no practical problem in this. But I do have available functions, and all of these functions will be doing some or the other thing and will try to give me the respective different words. So to get the words, I have word tokenize, and to get the sentences, I have sent tokenize. So look at this. Now I have multiple sentences. So for example, I have a sentence like this. Let us understand the difference between sentence and word tokenizer. It is going to be a simple example, and there are two sentences in this. So if I want this kind of a small paragraph to get converted into two sentences, which is the tokens for this paragraph, smaller pieces. So I'm going to split based on dot, the full stops, right? So if I call this sent tokenize, it is practically converting this into two sub pieces. This is my piece one. This is my piece two. It's going to split a text from a paragraph into multiple different sentences. So don't worry about this. Obviously, you can do some hit and trial, and you're going to be finding out things. But if nothing works out, obviously regular expression tokenizer will always work. So I'm going to use my own custom tokenizer. I probably have a very different set of patterns which I want to use, so possible in that. And then from this, I'll be practically using some bit of logical understanding here. So probably using a regular expression tokenizer, I'll be passing my own pattern, probably a word, a space, or a number or a digit. Based on any such thing, I want to split my sentences, I'm going to have that. Right? So the moment I'm going to use this, I'm going to have even the special characters being used. I can obviously specify my own custom tokenize. I'm using for the word part here. I can use the space part also here. So probably a space also will work as my split up predicate. So that is also 100% possible. Cool. Also pretty much you'll be able to learn it. I'm going to show it to you. So my first prime objective, if you have understood here, is to convert. So first step number one, if you could realize, is practically to have, I'm going to just put it like this. Okay, step number one is to practically have split up of bigger component of text into smaller blocks. So probably for words is going to be characters, but does not really make sense. For sentences is going to be words. For paragraph is going to be sentences. Okay, so that's going to be my step one. Now comes my step two. That's where we always have been doing things on my other data set. So when we talk about data analysis, so we have multiple different things. We talk about how do we clean our data? How do we perform the cleanups? That's where obviously the missing value treatment, the outlier treatment, so many things comes into picture, format correction, data type corrections and all that. But it's a text. So obviously the same concept will not work here. So probably I need to consume it in some different way. So for NLP, again, we have certain type of data corrections, which we end up doing. So out of them, the first is stop words. So what are stop words? So some common words that are present in the text, but do not contribute in the meaning of the sentences. So the most common stop words are a, and, the, in, are, am, on, all the conjunctions, the prepositions, I would say, are practically my stop words. So for example, I said, my name is Arpit Jain. So if I remove is from here, I'm going to still get the crux of the sentence, which is my name, Arpit Jain, still giving me the meaning. I'm able to understand what I'm saying. So these words like is, are, am itself does not have its own meaning, right? So that's where we end up always removing these parts, so where we end up having probably the ones where the actual meaning of my sentences comes into picture. Okay, so again, we have a list of those stop words already defined. So in fact, if you could see here from NLTK corpus, we have a function called as stop words. And stop words, again, is pretty much defined in multiple different languages. I think right now, it's supposed to, I think it supports more than 20 plus languages. So for example, I think French, Italian, even Bengali is there, I've seen it. So you can see the list of all those packages which it supports. I'm going to show it to you also. For example, here, yes. So there is a list of languages which it supports. So right now, Bengali, Danish, Azerbaijani, Arabic, German, French, Hungarian, Italian, Indonesian, Nepali, right, Russian. So you're going to support all these languages. So what it is, so practically it's a list of words, list of most common words which does not have its own meaning, like being, am, by, doesn't, having, or, here, out, did, can. So what we do is we end up removing the stop words by a simple function, like any word from this list which is not in my stop words. So if I do it, for example, I am a writer. So if I remove the stop words, am and a will go. So I'm going to left with only I in writer. So my next cleaning process is removal of stop word, which is practically I'm going to have all the common thing which is not required right now, which probably not be having any critical importance in terms of its meaning in my logical interpretation of sentences. I'm going to remove them. Okay. Fine. Now comes the next part, which is word nets. So now word net, it is basically now where we talk about the synonyms or the antonyms. So for the same words, I practically will be saying, for example, if I say, I have a dog, and then in the sentence, in the next sentence says, probably a breed of a dog, right? So I'm using dog, but in different places with different names, possible. So now there's a concept, because now the dog probably might be referred by different names in 5 different sentences, does not mean it's a different entity. They all 5 belongs to one single entity. So the machine should not interpret them as 5 individual entities, rather it should interpret as one single entity. So a concept of word netting comes into picture, right? Where we try to kind of combine them, give them a bigger umbrella, where I'm going to talk about synonyms and the antonyms, a group of similar set of words, which is going to give me the similar meaning. So in terms of synonyms, antonyms, I'm going to define the similar sets. Okay. So now here we have again a WordNet concept where we'll be using how WordNet will be come up. So I'll be showing you this. So for example, there's a concept of synsets, similar sets. So what do we do in this case? Whenever I'm going to pass a word, I'll be able to see the similar sets. So there's a group of such things. For example, here I can see this. So dog.n.01 is a group of, there's a pool of words already defined in NLTK package. I can also edit this, where I'm going to be able to see the different components from this. So similar words respective to my dog. That's like the way similar words coming up in this case. So for example, you're going to find out the multiple different things. For example, here, the dog barked all night. I have the definition also. You can see this, a member of a genus Canis, probably descended from a common wolf that has been domesticated by man since prehistoric times, occurs in many breeds. So you're going to be seeing probably the same example from the respective different similar sets. It's going to be giving me a pool of all those words which probably can be used in your text. So I'm going to mark them as one single entity. Okay. So if we go in more details, you're going to be seeing this. For example, here, if you can see here, I have a group called as canine and a domestic animal, and they both probably have dogs. right? And similarly, I'm going to look for the hyponyms. Hyponyms, I'm going to see multiple groups, so probably a dog, fox, hyena, jackal, wild dog, wolf, and more or less they are related with probably a canine teeth or probably falling under a dog category or a cat category. I'm going to put up all of these entities together. Okay, and then we ultimately end up having the lemmas where for the same thing, I'm going to talk about the synonyms and the antonyms. Again, I have an example here. So you'll be able to see multiple different things. For example, you can see this. I'm trying to get the lemma for travel. So you can see this: traveling, go, trip, move around, journey, locomotion, locomote, move, change of location, travel, traveling. So probably you will end up finding multiple different names for the same thing. So if in my pool of words, I'm going to see all of them, so it should not be marked up as different entities. Rather, it's one single thing, which is travel, right? So I'm going to provide a super group to all the common set of words. That's where the concept of hypernyms comes into picture. Okay. Similarly, for all those words, we're going to be finding out it's not only for similar sets. I'm going to look for antonyms, the opposite of that. For example, increase, you're going to see the antonym is going to be decrease, decrement, and all the things. So probably going to come up on that. So decrease and decrement are the two words which I'm able to get. So likewise, for every single word, you're going to be finding the respective antonyms and the synonyms. So basically, still all of this are pretty much part of my tokenization step. So once I have the tokens with me, I cleaned up the stop words, basically the overrepresented words from my text. And then on top of my major keywords, which I'm having in terms of entities, I'm going to give them a groups. I'm going to align them inside probably the supernyms where I'm going to have the similar words, or the opposites of that. I'm going to give them a tag. So in terms of where now I can identify each word, if it is being represented in a different name in a different pool of word, probably I'm going to give them the same entity. It should not be identified as a different text. Okay, that's where the concept of this comes. In fact, one more cleanup process, a very important concept that comes into picture is stemming and lemmatization. Let me share my white screen. I'm going to give you an example for this that'll make more sense. I'm sharing my white screen, guys. So I'm coming back to my text. Probably I'm going to add a new slide here. Okay. So my next very important concept is stemming and lemmatization. Very important concept. So now we talk about the verb forms. For example, I say fly. Flying is a verb form. Flew is a verb form. Flown is a verb form. I'll say cry. Maybe crying is a verb form. Cried. Right? So all of these are verb forms. But my core root word is this. Right? So if I have multiple verb representation also of the same key root word, I probably need to understand it still means the same thing. So probably flying, flown, flew, they are not three different entities. They belong to one single class. Right? So now even this is important to understand the verb forms of my text. That's where NLP becomes a little tricky, because now we have to understand the grammar also, right? So that's where we have stemming and lemmatization comes into picture. Okay, so both of them, it does the exact same thing, which is the concept of giving me the shorter form of this, but the concept is different. The way they do it, that's different. I'm going to tell you the example. For example, if I talk about stemming, right, and lemmatization. So if I have a word, say flying, so what is the stemming? It practically chops off the suffix. So whatever my suffix is, here in this case, my suffix is ing. You can see this, ing is my suffix. So what stemming does is gonna chop off the suffix. Simple removal of suffix. So for flew, what is my suffix? Probably EW could be. Let's see. For flown, probably N is my suffix. So if I convert flying using stemming, I'll get fly. If I use probably flown, I'll probably get flow. If I use flew, probably I'll end up getting FL. Can you see this? So by simple chopping of my suffix, probably is not the right solution to get the root crux, the main word here. So because in each of my formatting of the verb forms, probably I will not get the right keyword by only removal of my suffix. On the other hand, lemmatization is the process in which I'm going to get the dictionary root word. So for each one of them, flying, flew, and flown, I'm going to get fly. Because that's the dictionary root word for these words. So that's how the conceptual part of stemming and lemmatization works. So stemming is gonna only simple chop off my suffix, no logical understanding there, simple removal of my suffix on that part. Where lemmatization, it actually refers the dictionary in the backend, and then obviously it has a dictionary loader there. And from that, it's gonna find out the actual root word from your dictionary. What do you think? Stemming is more logical or lemmatization is more logical? What will you do, guys? Probably I need some comments. What do you think will make more sense to your way of learning? Stemming or lemmatization? And I think, and trust me, guys, in fact, both of them has its own respective pros and cons. So obviously, right now, if you're seeing, probably lemmatization makes more sense, right? Because I'm going to get the actual root word here. But in real scenarios, you still end up using stemming. In some cases, I'm going to probably give you some examples on top of that. In fact, I do have some examples. Let me share back my screen. I'm going to show you that. I'm coming back to my code part. So I'll be showing you how each one of them is represented. And in fact, I have multiple different packages which does this part where I'm going to do which one is important for me. So for stemming, I have majorly three types of stemmers. There's something called as Porter stemming, very old fashioned and gentle. There's a Lancaster stemming. It was developed by the Lancaster University, more aggressive. And there's a snowball stemming where I have, it is also called as more Porter 2. So advanced version 2 of my Porter stemmer. And obviously you're going to see the difference in all of them. And if nothing works out, regex. So in NLP, you probably always going to see a regex. So regular expression, or you can write your own custom functions. Okay. So for example, I'm passing 8 on Porter stemmer. Can you see this? I'm getting ATE wrong because the root word is eat, right? Then I have Lancaster stemmer, I'm getting AT. And snowball stemmer, I'm going to still get it. So, and they all are wrong. I want eat here. So probably if you pass lemmatization on top of it, I'm going to get 8. So now you can ask me how to identify which one is good for me, Lancaster, Porter, or snowball. Trust me, guys, you end up using probably all and see where you're getting the best results. So there are the multiple types. All of them have certain rules, some codes in the background, which does the stemming job. And then you can see this here. I've written a few more examples of fairly. So fairly, fair, fair, right? Then loudly, you're seeing LI is wrong, right? So in fact, salty is anyway, no one is giving the right answer. Okay. So there are certain drawbacks of stemming, obviously, because it simply chops off the suffix. Probably the output of a stemmer might not be a logical word itself. For example, here, SALTI is not even a word. There's no meaning of this, right? So likewise, stemming can end up giving a completely vague word, which not even exist possible. Okay. Now that's where lemmatization comes into picture. So you're going to be seeing a direct function called as WordNet lemmatizer. I have directly available in this. So whenever I'm going to call the lemmatize function, you can see it's going to give me the root word. Belief is the root word of beliefs, right? Likewise, you're going to find out. So in fact, I've given multiple different examples. You're going to see every single time you're going to get the right answer from lemmatization, because it practically ends up using the dictionary root word for me. So all the respective words end up giving me a dictionary root word. Okay. Regex is fine. You can always R&D on top of this. Cool. So the now next very important topic is part of speech tagging. So now I have identified my individual root words. I have also identified my multiple different the main meaningful tokens from my text after removal of my stop words. Now the identification of parts of speech. You remember in your probably in your school days you might have been talked about noun, pronouns, conjunctions, adverbs, adjectives. So now the next task is the text, the machine should understand what is an adverb, what is an adjective, what is a noun, what is a pronoun, and based on that, it should give me the logical connectors. Because machine should understand the meaning of my sentences also. And the machine randomly cannot understand this. It has to develop some patterns. So that is where POS tagging comes very important. So with the help of this, it's going to give me the actual part of speech tags. For example, nouns, verbs, adverbs, adjective, conjunction, and their respective subcategories. Good part is we already have a direct function for all of this, so you don't have to practically do it manually. But there's a whole extensive list of tags which are present. Okay, so I'm going to quickly read out few of you. For example, JJ is adjective. I have JJR comparative. JJS is superlative. Then I have noun, plural noun, proper noun, plural. So, and you can see this personal pronoun. I mean, so many things: adverb, particle, verb, right? So, verb also in past tense, present tense. You're going to find all those tags. Okay, and obviously now once I run this word POS tag on top of this word tokens, which is I'm going to school. Can you see this? Now all of this individual tokens are now getting tagged. For example, I is a proper noun, am is a verb, and going is a verb. VBG is participle, present participle verb. To is to, school is I think NN is proper noun, noun singular, right? So I'm going to get that. So we're going to see all of this is now being tagged by giving the actual part of speech values for the characters. Right, so that's pretty much what you're going to find out here. So all of this is going to be simply done with a direct function here, which is POS tag. So POS tag or part of speech tag is going to give you the tags for individual characters here. Okay. Why do we use POS tagging? Multiple different use cases. So this concept of machine translations. You heard of probably this. The real-time translators, like I'm converting what to say, an English sentence to a Spanish sentence, Google Translate. It has to understand the grammar there, right? If it does not understand the grammar, I won't be able to translate, right? So very practical use case which you also see on a real-time basis, like the ChatGPT or the LLMs, they also practically use a POS tagging in the background to identify the sentences structure. Obviously, the speed is very much faster because the training has been done in such a way where the results are very fast. But the machine also ultimately uses the basic concept of POS tagging there, which is understanding the parts of speech. Okay. Cool. So that's perfectly fine. I'm gonna, okay, this is fine. We can skip this for now, not mandatory. Yes. Okay. I think we can talk about the parsers as well. In fact, this POS tagging is also used in terms of parsing a sentence, but that's okay. That comes in full-blown sentences. That's okay. We can skip this part. So what I'm going to talk about is practically how you use or consume this information of individual pieces into my actual day-to-day business, right? So once I have the individual synonyms or individual part of speech tags present, now my actual task is to run the translators on top. It's probably a training process. When I say machine learning, right? So machine learning is a process of finding the patterns between my individual features. You already know that, and how the patterns are being identified. It's more like a numerical equation in the background. I know that if a linear equation is going to be y is equal to mx plus c, and probably I'm going to have beta naught, beta 1, beta 2, depending on the number of parameters, right? So everything ultimately boils down to a number. Ultimately, it's a number in the backend, right? So now, after doing all the cleanup process of my text, the very important step which comes towards the later half of my NLP process is called as vectorization. So vectorization is that process which converts the actual text to numbers now. So to have the learning process done, to have probably a data set where now a machine can understand. Machine can understand in terms of 1 and 0, right? A binary language. So for that, I have to first convert the data to a number format. So all the equations, the mathematical equations, can only be converted in terms of numbers. So a process where I'm converting text to numbers is called as vectorization. And I have two proper broad ways in which vectorization can be done, but there are other types of vectorizers as well. Okay. The two prominently used vectorizing technique are count vectorizer and TF-IDF vectorizer. Very, very prominent concepts, guys. So I would want your attention here. So count vectorizer and TF-IDF vectorizer, very important concept. So how this works, I'm going to give you an illustration also how this works. Okay. So I have written down two sentences. So corpus is basically a collection of all the documents features. Okay. So what happens in a count vectorizer? Let's understand this. How this whole thing gets converted into this. You can see the 0, 1, 0, 1 coming up here. So what is this? How it is coming up? I'm going to show you that. So suppose I have two sentences, or basically two corpus or two sentences. First is dog hates a cat. It loves to go out and play. This whole thing is my one sentence. And the second, one document or a corpus. And the second is cat loves to play with a ball. So here you can see this. Practically, I have two documents. So what a corpus means here, a combination of all the unique words from this. So what are my unique words here? Dog. So dog is coming only once. Cat is coming twice here. Can you see this? So cat is going to be coming only once. So from all the proper tokens, from whatever values we have here, all the words from individual sentences, I'm going to convert them back into a group of unique words. So this group here, and, ball, cat, dog, go, hates, it, loves, out, play, to, with, is basically having all the unique words from these two documents. And it is also called as feature vector. So feature vector means here, all of this is now gonna be coming as my column names. Can you see this? And, ball, cat, dog, go, hates, it, loves, out, play, to, with. And this is all coming as my proper columns. Is it visible to everyone? The same unique words actually becomes my feature vector, which is practically my columns. If you see in terms of data, they are becoming my columns here. So all the unique words here in general now will turn up into a column. Okay. Now what we do on top of it, bag of words. So basically takes a document from the corpus and converts into a numeric vector by mapping each document word to a feature vector. So for example here, so what we end up doing is we practically end up finding the vector wherever I have this present. So for example, if I talk about my document number 1, which is this, dog hates a cat, it loves to go out and play, right? So I have dog present, so dog will come out to be here. So dog is 1, 2, 3, 4. So 1, 2, 3, 4. This becomes 1. Then I have second column as ball. Do we have ball here? No, we don't have ball here in the first document, hence becomes 0. The next column is cat. Do we have cat in this? Yes, we do have cat. This becomes 1. Do we have dog in this? Yes, we do have dog. Hence it becomes 1. Likewise, here it is 0. That means with. Do we have with here? No, we don't have with. Hence it becomes 0. So simple 1 and 0 mapping of all the unique words. If it is present in this feature list, if it is there, it's going to turn out to be 1. If it is not there, it's going to be 0. Similarly, I'm going to having a document representation for 2 also, 0, 1, 0, 1. Is it making sense? Everyone, are you getting it? How the data got converted? I'll share my whiteboard. I'll quickly show you how ultimately data will look like. Okay, so suppose I have my document 1 and document 2. If I convert them into a data table, so it'll look something like this. So all the unique words, word 1, word 2, word 3, word 4, word 5, and then I'll be, suppose if only two documents, when two rows will come, document 1, document 2. Suppose word 1 is present here, so 1 0 1 1 0 0 0 1 1 1. So this is how my final table will look like. Is it making sense? After count vectorizer, how my document, how my Excel file or simple, you can say table looks like. So on the column names, I'm going to have the feature list. And in the rows, I'm going to have the count vectors, the count calculations of 1 0 1 1 0, wherever I have that particular word present in the overall document, I'm going to give 1, else 0. Yeah. So that's what happens with the count vectorizer part. Okay. Obviously, it can have certain other things. I have another strategy, TF-IDF. So what it does, let's quickly understand. There's again a logical understanding of TF-IDF. Okay. So now for TF-IDF part, this is called as term frequency and inverse document frequency. It takes two individual concepts. It first calculates the term frequency for each unique words. Okay. So now, for example, here, this term frequency of individual word means number of times that word appears in the document divided by the total number of words in the document. For example, if this is my document, which is say this, cat loves to play with a ball. So how many words are there? Practically 4, 5, 6, 7. So if I remove A, I will have 6 words there. So in this 6 words, I have cat coming how many times? 1 times. So term frequency of cat becomes 1 by 6. Getting it? Yeah, so you can see this. It has 7 words, but A has been ignored, obviously, because it's a, I'll be removing it using the stop words technique, right? So now here, first, the term frequency is getting calculated. For each word, I'm first going to calculate my term frequency. Then there's a concept of inverse document frequency. That's where the formula is log of number of total documents divided by the number of documents with the word in it. So how many total number of documents we have? 2 documents I have. This one, document 1 and document 2. And in how many words, how many sentences I have the cat present. So both the sentences I have cat present. So log of 2 divided by 2. So practically I'm going to get log of 1, that becomes 0. Right? So if any word is getting over-represented, if any word, generally it is very useful for words which are over-represented, like is, are, am, the conjunctions. So if any word is over-represented, I'm gonna get penalized for that. Okay, so it's gonna give me penalization factors. So this is giving me more logical answers. So if anything which is more practically present, I'm gonna get a 0 for this. So log of 1 by 1 is gonna be that, right? But it's going to give me simple formula is log of total number of documents divided by the number of documents with that word in it. And ultimately, then the TF-IDF becomes multiplication of both of them. So 1 by 6 multiplied by 0, ultimately I'm going to get 0. And likewise, it's going to get done for each of these unique words, And ultimately, instead of having only 1 0 1 0, you ultimately end up having more concrete values here, with kind of a definition of representation as well. If anything is over-represented, I'm going to get zeros, you know that, or values closer to 0. And if something which is probably lesser represented, I'm going to get higher value because log of that will be higher, right? And ultimately, that's going to give me more of a representation where I'll be saying that this value is more popular, more prominent, right? So that's what we're going to talk about it. Okay, so that's going to give me the feature importances as well. So this is a technique, TF-IDF helps us do the feature importances for my text as well. And ultimately, once we have this, now I'm going to practically have the data set, which is now I'm going to go in terms of different values. So ultimately, I'll be having an Excel file And that Excel file now can be further trained on top of a completely new machine learning training process. So if I share back my screen on terms of this one, just give me a minute. Yeah. So now what happens at the end of vectorization process, I end up having an Excel file like this. Okay. So I'll be having multiple different columns, and then in this I'm going to have multiple different rows. So each row here means one document, and for document here, and this set of column means basically feature list. And as you can understand, if the number of documents increases, the number of unique words will obviously increase. So generally NLP is a process which is very much column heavy. I'm gonna generally get probably 5,000 or 10,000 plus feature list. Possible, right? I can have 5,000 unique words in my document, possible. So this generates those many columns, right? And ultimately with the help of these columns, I'm going to be seeing the respective different details, right? So now, whenever I have this file, I have the respective different columns here. Now on top of this columns, how can we use it? So probably this set of columns which I have here. Now how I'm going to consume these columns. So any machine learning strategy which will be used. So generally, in general, whenever we train NLP process, I obviously going to have a target. So probably some bit of class. So this text is going to give me some class or some ultimately target here. And then we're going to be using the machine learning method, the supervised methods on top of it. I can also use unsupervised if the target is not available. But ultimately, this NLP now get converted into a simple Excel file where I have certain rows and I have certain columns and everything is in numbers. So if I have a target, I'll end up using the supervised methods. And if I don't have a target, I end up using an unsupervised method on top of this. And obviously, supervised methods, I also have multiple different ways. But in very general norm, we end up using naive Bayes. It has been observed that naive Bayes works very good with NLP process, because if you also logically understand, naive Bayes also does the probability or more like the frequency kind of a calculation here. That's the logic of naive Bayes, right? And in fact, if you also understand, the moment when I did this tokenization, I ultimately end up using some bit of frequency calculation also. So this logic is pretty much in sync with the naive Bayes logic. So it has been observed generally that if I have a target available here, so we end up using naive Bayes, that's gonna, it generally gives us good performance in my machine learning methods. So that's the whole crux and the whole base of your NLP process, guys. So right now, what we use on top of it, like with the moment we have a data, we can obviously run any machine learning model on top of it to get the results. But as I've said, naive Bayes is prominently used. So that brings up the base for any NLP process. Now, when I talk about the advancement of NLP process, what changes is practically the process of training. So the whole concept which I just talked about, where cleaning process and all that, that is still pretty much there. I did not change anything from the cleaning process, honestly. That's still pretty much there. Now, once I have the clean data, now on top of this clean data, how the training has to be performed. I have to use a transformer model, so I can do that. If I want to use a BERT model, I can do that. I want to use probably something else, I can do that, right? So the training process differs, but the whole crux of my NLP remains the same. That's why the cleaning process, the pre-processing part remains the same. Clear? And now probably in the upcoming videos, what we can do is we can go in detail in terms of training methods as well. So till now, we just talked about how did we prepare the data, because training is pretty much now on top of it. So training also, I'm pretty sure machine learning, you've already learned it. So in terms of machine learning, all the methods can be pretty much straightforward applied, because it's going to be a simple Excel file. Y and the X, I can apply the formulas, I can load up the functions, I can run it. But in terms of advanced models, probably running a transformer model on top of it, probably running an LLM model, large language model. I have multiple different languages to be trained. I can do that. So all of this training will be done respectively, guys. Any questions? I'm open to questions. Anything which you want to ask? Yes, I'll share the notebook, Nandini. So you'll be getting the link, so they'll get updated here. Don't worry. Any questions, anything which you want to ask? I hope that clarified the concepts of NLP to everyone. Cool. So if we are fine, so probably we can call it a day. So I try my best. What is a language model and how they are built? Language model is now in these days what we do is, if you heard of large language models, right? So what we do in terms of that. So instead of giving the direct training sets in terms of that supervised method, I have a target and things like that. So what it does, it takes the individual raw text as my input, right? So that's a different concept. So where we talked about a large language model and how it is built. Built is basically again a concept there. So LLMs have their own set of concepts. So what it does again, builds up the feature maps. So like the way we did here, like vectorization, ultimately converting things into a number. So all the learning has to eventually happen on numbers only, right? So it does the feature mapping of all of these things, but the core concepts remain the same. So probably again, it has certain few other conceptual part. I'll try to cover that in the next session. But in general, if I have to answer that, like the whole concept of a language model is, I'm going to give an input. For example, if you use a chat GPT model, what it does, I'm going to give it a text. So it understands the concept of that, the meaning of that question, and responds accordingly, right? That's a language model. So language model means I'm going to give a language, probably what I know as an input to the system. It should respond back on that language which I have. That's actually called as language model. And for that, again, there's a whole set of logic involves in the background. So that's basically the advancement of NLP, where the language models comes into picture. Right. So we're going to talk about that as well with time in the subsequent videos, where probably now how a feature mapping is done on language models. Again, there's a bit of mathematical concepts behind that. Make sense? Any questions? Any more questions? Anyone? Okay. Well, thank you so much, guys. Wonderful talking to everybody again. So yes, the notebook will get updated here. Don't worry, and it will be there in the thumbnail section. And thank you so much. It was a pleasure talking to everybody. We'll come back again with a new set of video where I'll be going in much in detail in terms of language models. Okay, we'll do that. Thank you so much, guys. Have a good day ahead. Bye.